Okay, bonding in metals. We've talked about ionic bonds, we talked about covalent bonds, we'll talk just briefly about bonding in metals. So the model we use here is called the electron sea model, like an ocean of electrons. So we learned that metals have low ionization energies, which means it only takes a little bit of energy to pull an electron off of a metal atom. What happens in a metallic solid is that each metal atom donates or loses one or more electron, and those all go into this electron sea, or this big pool of electrons. So here we have individual sodium atoms, and they're all donating an electron to this collective sea of electrons. So they're sodium ions, but they're surrounded by a negative electron ocean. So those positive ions, which would repel each other, are actually attracted to the negative sea of electrons, and so they stick together. I think of this a little bit as like a neighborhood. You know, they say it takes a village to raise a child. So if you think about each of these sodiums as a house, and everybody's sending one little boy out to play for sodium. And so the little boys are going all over the neighborhood. This is like when I was a kid and we were allowed to do that. You just run all over the neighborhood. But everybody's kind of watching out for all the kids, right? And so it holds the neighborhood together. It bonds everybody together, if that helps you. This model does explain conductivity. In order for a metal to be conductive, there must be some charged thing that can move. In metals, it's the electrons that can move. These electrons are not localized on any individual atom or ion, and so they're free to move around. And so we can have electrons moving, and that's what conducts the electricity. It also explains malleability and ductility. Malleability, they can pound it into a sheet, or ductility, draw it into a wire. You hit a piece of metal with a hammer, and it doesn't shatter. It just dents, right? And you can just keep denting it until you have it the shape that you want. This explains it because the attractions between these individual ions are not directional. There's a collective attraction to the overall sea of electrons, and so if we move some of these out of position, it doesn't really affect how tightly they're attracted to each other. They can just get deformed and it's fine. In an ionic compound, where you have very directional bonds between the ions, if you apply force, like hitting it with a hammer, what will happen is a piece will just shear off. It'll just break, or it will just shatter, because you've disrupted the bonds and they just give up. Okay, so that's bonding in metals. Any questions? And then this is a little bit at the end talking about ozone. And we just looked at the structure for ozone. I'll draw it up here real quick. So there's ozone, and here's oxygen. This actually is a resonance structure, and so it's not a double bond and a single bond. It's really more of a 1.5 bond on both sides. A 1.5 bond is stronger than the single bond but weaker than the double bond. So the bonds in ozone are a little weaker than the bonds in oxygen. So the ozone layer protects us from excessive ultraviolet radiation, because as the UV radiation from the sun comes in and hits the ozone, that UV light has enough energy to break that hybridized, well, shouldn't use that word, that bond in ozone, which is not as strong as the double bond. So it can break that bond, and it will make, when you break, actually let's do it this way. I didn't mean to do that. I'm making this up as I go along, can you tell? Let's just ignore lone pairs for now. So there's the oxygen, and what we have with the ozone is, it's harder to do than you might think, is like a 1.5 bond. So these bonds are not as strong as in the oxygen. So the UV light comes in here and it has enough energy to break this bond. And so what you get then is you get an oxygen molecule and you get an oxygen atom. That absorbs the ultraviolet radiation. This oxygen atom is not happy at all, and so the ozone reforms, and then it's ready to absorb some more ultraviolet radiation. The issue that we're having with our ozone layer is some compounds like chlorofluorocarbons, when they get into the upper atmosphere, they disrupt this process, and so the ozone doesn't reform, and then that causes a problem. Any questions?